Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. So, uh, before we start, who attended the talk of Osama Khatib today? 1, 2, 3. Okay. For those of you who did not attend it, you missed a lot. Okay. So this was part of the Smile conference today. You can ask the guys about their impression afterwards. If we have some time in the end, we can discuss. The most thing that impressed me a lot is the last thing he said is that everything he showed today is model-based control. That's like, it's a relief, okay? So more on that later if you want to know, for those who did not attend the conference. Second thing is the projects. Are you done choosing your groups and your projects, the robots you want to work on, or not yet? See, half. Everyone done? Not yet? Okay, if you're not yet, you have to hurry up because you're losing, the choice to choose your team members, and you're also losing the choice of the projects. The projects are all already online. You have 6 projects. You have to choose in the end 5 among us, all of you. More on that will come later, inshallah. But for now, you just need to choose your team members and the project. That's the deadline for this week, inshallah. There's the spreadsheet. You can go immediately and just write you and your group's names, and you can choose the project from what's already listed there. You all finished the assignment? Okay, was it clear? Okay, so hopefully now you get this idea of what's the relation between the homogeneous transformation matrices we're talking about and the fact that they're actually mapping points from Rn to Rn. Okay, if you have a 4x4 matrix, then we're talking about mapping from R3 to R3, which is in the space we're living in. And today, inshallah, we're going to be continuing on last lecture, which is on the rigid body kinematics. So we're going to have 2 lectures on rigid body kinematics. Today, inshallah, hopefully, we'll be able to finish the whole discussion. Next week, we're going to have 2 lectures on rigid body dynamics, and this will be it, okay, for topic number 2. Afterwards, we're going to be seeing how we can start connecting rigid bodies together to talk about manipulators. So a recap is that when you start with a robotic system, okay, such like the one in the figure you see here, you start by saying, okay, I have a frame attached to every object of choice, or object of interest, the base of the robot, the end effector. You can have a frame on every link, okay? Usually we're going to be doing that later. You can have a frame on the target, an inertia frame, and so on and so forth. The relative pose of any 2 frames, okay, is given by the pair of the rotation matrices and the translation, okay, vector in R3. And if we combine them in this, okay, form of a 4x4 matrix, then this is what we call the homogeneous transformation matrix. And then we said that the homogeneous transformation matrices, you can easily follow this rule to map any frame to any frame. Okay, you can easily, okay, if I'm interested in the end effector's frame with respect to the inertial frame, and I have the end effector's frame with respect to the target frame, and I already know the target with respect to the end effector to the inertial, I can combine all of these pieces of information. You can combine 2 homogeneous transformation matrices to get a third one, and they have to follow this order, okay, because it's not commute, okay, it's not commutative. SE3 and SO3 are not abelian groups, which means they are not commutative, so the order matters. Yes, Fahd. Yeah.
K on top and J compared with writing K and J, and both are on the bottom?
Both on the bottom. So this is just a flavor. If you go to the book, okay, so the book by Frank Park and Kevin Lynch, you'll find there that actually they write all of the indices down. Okay, they also have a similar way of canceling. So so for example, it will be KJ and this will be JI. So the J will match with the J, and they also cancel out. This is just a flavor. Some people even write the I here and the J on the other side. Okay, I prefer this notation. Okay, you also find another thing in the book different from here. They use a capital T for the transformation, not H. Okay, I prefer to use the H. Okay, the T is used when I first started, writing stuff. I used the T, capital T, not for the transformation but for the twist. Okay, and we had a mix of you're gonna find a lot of references. This is the stuff I settled about in there, because the capital T is used actually in many ways, being the tangent space, the tangent bundle, and something today we're going to be looking at, which is the tangent map even. So there's a lot of, you use the T a lot. So that's why I just want to relieve the notation from this. So if you want, for example, the J with respect to K, this is exactly the same as k with respect to j, but with an inverse. And this inverse, you don't need to memorize any hard rules for the 4x4 matrices inversion, but it's simply given by the matrix that you see here. Okay, because everything here has physical meaning. You had the assignment, so you've seen that. Okay, this pair correspond actually to going back and forth. You know, the inverse of the isometry map, and the H itself is actually when you combine two homogeneous matrices. So you've seen the product rule of SE3 is given by an isometry acting twice and so on and so forth. So this is hopefully what you should be convinced with, okay, from the assignment. Whatever happens in physical space, okay, we're going to be mapping it back and forth to this abstract picture. So this is just an abstract picture. This is not SO3 really. So SO3 is not a surface that you can visualize in 3D, because in fact, it's a 3-dimensional manifold. So in order to visualize it as something, you need to actually put it in a 4-dimensional, R4, so that you can visualize it, but that's not possible. So this is just an abstract picture, but it will help us a lot to, whatever we say here about about SO3 abstractly will hold to any other Lie group. Okay, it's just that the name of the group will change, the nature of each one of these, points and the tangent vectors and the algebra elements, they will all change, but abstractly everything will remain the same. Okay. Question? No. I'm the R4 ends in 4 numbers, just a vector with 4 numbers. Okay. What you visualize here is like a picture. So if I give you you see this because it's a 3-dimensional object, right? In 3-dimensional space. If I tell you, imagine for example, a 4-dimensional sphere or a 3-dimensional sphere, you cannot visualize. You can only visualize a 2-dimensional sphere. That's the idea. Okay. So if what we did last time is that we looked only at SO3, okay, and because it's easier to work with. So SO3, this is the physical information. Okay, this is what the physical meaning and the concepts in the physical space, and this is what it means on the abstract manifold, and this is the notation we use. So if I have 2 frames, B and S, for example, then the relative orientation of these 2 frames is simply a point on the manifold, and we denote it by R. Okay, so it lives in SO3. If I have a smooth sequence of relative orientations, okay, so if B with respect to S is moving, so I have a smooth sequence of relative orientation between B and S, then we have a smooth curve on the manifold. And this is simply given by the curve on the manifold, gamma R. And the rate of change of the orientation is simply what we call R dot. It lives in the tangent space to R at the SO3. And this is an element of the tangent space. And the element of the tangent space is also a tangent vector to the curve. Okay. Then last time we talked about, okay, where is angular velocity? Okay, so how do we talk about angular velocity? Angular velocity lives at the algebra. And we said that the last time that the algebra is simply the tangent space to SO3 at the identity. And the tangent space itself at any point R was given last time that when you multiply the vector transpose multiply by R, you get a skew-symmetric matrix, and we showed it last time. And if you have that R is the identity, okay, then in the end, we just have elements that are skew-symmetric. So the space of skew-symmetric 3x3 matrices is exactly the tangent space to SO3 at the identity, and this is exactly what we call small SO3. And this has a special name. It's called the Lie algebra of the Lie group. Every Lie group has its own Lie algebra. Okay? Whereas the Lie algebra, it's always the tangent space at the identity. So always keep that in mind. This will hold for any tangent space. It will hold for any Lie group. In this case, this is where velocities live. And R dot is not a velocity. Omega tilde is the velocity. Last time we called it capital omega, but that just was the name of the element. From now on, we're going to be calling it omega tilde. Yes.
This means that always any rotation starts from let's call the identity and
you always have an identity group. Yes, you always have an identity element.
this rotation starts from the
You
identity.
can always relate it to the identity. There is a way. Yeah, you can any rotation matrix is like you took the identity and you rotated it. Makes sense. It's just like any vector. If you have any 3 numbers, for example, 1, 2, and 3, I can always link it to the 0, 0, 0. Makes sense. Exactly the same idea.
Because the angular velocities are only present in the identity or at the identity.
At the identity, yeah.
Yes. Doesn't that mean for any rotation to have an angular space, it needs to start at the identity?
No. You should not think about it this way. No. I can start from like here and I move like this.
Why does it say here that it has to start with the identity?
It doesn't say it hasn't defined identity. What it says here, it's a good way of thinking, but it will take us some time. But what this says is that you actually see it here you can actually see it by just comparison. That's a question. So is R dot, which is an element of the tangent space, is it the dot of some R? It's trivial R, right? Is omega the dot of some R? Or omega tilde, is it the dot of some R? No, no. It's not. In other words, let me rephrase it. Omega tilde is not the tangent vector to any curve. R dot is a tangent to a curve. You see it here from the picture. But omega is not.
The curve defined as a change in orientation.
That's right.
That's what's defined.
And we're always going to point, this whole curve will be a point here identity.
Shouldn't the tangent be the straight away? Shouldn't the tangent be that speed? Yeah, why here?
No, that's different. Yeah, that's the misnomer. Rate of change of orientation is something completely different from angular velocity. Yep.
Change when you take it to R, it's a change in orientation.
That's right.
No matter what.
Yes, right.
Shouldn't it be the tangent on the curve? Yeah, shouldn't
You're reaching there. It's a very good exercise. You need to see it with your eyes, and that's inshallah what you're given the homework. Okay, you're gonna see it with your own eyes. That is, this object we're talking about is what you used to call, okay, what you took in any mechanics course as the angular velocity. But R dot is not the angular velocity by itself. Yes, Ibrahim. No, R is simply orientation. We're only talking about SO3 here. We remove the translation completely. We're only thinking about frames that change where they are. So no translation. Yes.
Saying R dot is tangent to any point on the curve.
On the curve.
Is omega tilde changing with points on the curve as well?
Yes.
Omega tilde
Yeah. That's why you see I put here a subscript T. So for example, RT will be the point here you're talking about. R dot will be the tangent at that time, and omega tilde will be at that time different from, okay, at every time. But it will change directions only. It will always be in this space, always at the identity.
Changes its direction and its
and magnitude. That's right.
it's not a tangent.
And it's not a tangent. Yes, exactly. But it's a vector. It's a vector, but not a tangent to a vector. You see, that's why we have tangent vector to a curve, which is something, and we have elements of a tangent space, elements of a vector space, which are called vectors. So it is a vector, but it's not the dot of anything. And will lead us to something, but I don't want to discuss it now. I'll have to keep that for maybe if we have time, ask me again, which is related to gyroscopes, but I'll not say anything about it now. Okay. Yes. Yes. Yeah. Changing magnitude. So as an abstract vector, it goes, bigger or small for different points. Exactly. Yes. Absolutely. Yeah. Of course, that's what we're going to discuss today. The question is now the natural question. How is R dot related to omega tilde? That's what we're going to be doing today, inshallah. That's the whole topic of today. But before that, take that same abstract picture without any extra math. And you see, this is the power of the differential geometry. Can we do the same for SE3? We said that this picture that we had for SO3 also is valid for any Lie group. Of course, now we're talking about SO3. You know what rotations are. Why don't we talk about also relative poses? So a relative pose of any two frames in 3D now will be a point on a manifold. This manifold is SE3. So it will be a homogeneous transformation matrix. And a smooth sequence of relative poses will be a smooth curve on the manifold. If you have a rate of change of the pose, it will be also an element of the tangent space, H dot. And now we're going to have a new, object we're going to be introducing. You're going to be seeing it for the first time, and it's the whole course is based on this object. It's very important to really understand what it is and how you play around with it, which is known as the twist. The twist is nothing else than a fancy way of saying generalized velocity. Translation velocity and rotational velocity at the same time. So linear velocity and angular velocity in one object. Okay? We just call it a twist. So it will also be an element of the tangent space at the identity. which is a vector in the Lie algebra. And the Lie algebra here is called SE3 for capital SE3. Did we say anything new? Just it was very easy for me to create this slide, right? Just copy paste of everything and just change the notation. Also thinking about it is exactly the same. The math will be different. I mean, they will look different, of course. In the same way that H matrix is a 4x4 matrix and the rotation matrix is 3x3 matrix, things here will have different dimensions. But there will be a lot of commonalities, and you're going to be seeing exactly how they are copied. There's a lot of similarities from a mathematical point of view. Wait, so there was a question here first.
What's the dimension of let's say dimension of rotational angular velocities?
Angular velocity is there, so the omega tilde. The omega tilde, does anyone remember what will be the dimension? You can actually see it from here. What will be the dimension of an element of SO3? A 3x3 matrix, a skew-symmetric 3x3 matrix. And an R dot is what? Is also 3x3 matrix. And R is also a 3x3 matrix. And for these, can anyone guess what about the H? 4x4 matrix with a special order. You had zeros and one at the end. What about H dot? Also 4x4 with another special structure. We're going to be looking at it. What about the V tilde? 4x4, yeah. That's it. With also a special structure. It will have also some zeros, okay, there. No. It's not necessarily. Last time, that's exactly what we did. We showed that indeed we had the tangent space to SO3 is skew-symmetric, okay? Especially at the identity skew-symmetric matrices. And 4x4 and for SE3, it's not the case. So, you know, we're going to be seeing what structure exactly it has. We have to derive it, okay?
They can be, but it's not obligatory.
They are not. That's it. They are not skew-symmetric matrices. SO3 consists of 3x3 skew-symmetric matrices. SE3 is something else. You're going to be seeing what it is today, inshallah. Hopefully, okay? If you just allow me with fewer questions, okay? So today I'm gonna be introducing to you something very abstract for any Lie group. Okay, I'll try to be a little bit fast. You have to go through the math. There are just a lot of repetition here. Everything we're gonna be doing from the right and from the left. You're gonna be seeing what we mean by that. There's what Ammar, right? So Ammar posed the important question. If I have any tangent vector at a tangent space to a point H in any Lie group G, which is, can I relate it to an element of the Lie algebra, where G here is by definition the Lie algebra, which is the tangent space of the Lie group at the identity. Make sense? So we can do this using two maps. We're going to be introducing them right now. One is called the push forward of the left translation map, and the other one is called the push forward of the right translation map. So you see the result of commonality. There's something called the push forward of a map. We're going to be understanding what this is abstractly. Then we're going to be seeing what is the left translation map, okay, for a Lie group, and what is the right translation map. Okay. So what is the left translation and the right translation maps? Consider any Lie group, any Lie group abstractly, G and its operation. If you fix an element H in this Lie group, then the left translation map is simply, it depends on the H. You see, that's why we write the H here in the subscript, because I've already fixed the H. I chose one H. And I'm going to be mapping G from G to G. How is that? You give me any point Q on the Lie group, and I'm going to simply multiply it from the left by H. This is how the map is defined. Did we introduce anything new? No, we're just playing around. By the way, you see this a lot in math. If I give you for example, you remember this operation? It takes two elements from G and it give you a third element in G, right? If I fix one of the two slots of this one, I'm going to creating a new map. Okay? Here I fixed the one on the left, and it's always reading, you know, like this. And in this case, I fixed the element on the right, and I'm always eating the Q like this. Take a look at it for a second. Does it make sense? So you see here, we started by saying for a given element, if you choose one H, okay, then what do you get? If I'm always multiplying, okay, from the left, any point in G by H, any point in G, which is here denoted by Q, by the same element H, what do I get? I can just get a map from G to G that will eat a point Q and will give me another point called H multiplied by Q from the left. Here, you remember this was called the binary operation or the multiplication. Of course, in the case, you can always you simplify it a little bit for yourself. For SON and SEN, the one we're working with, what was the group operation? What the matrix multiplication. And all of the points here of G were matrices. 3 by 3, 2 by 2, 4 by 4, it doesn't matter now. Okay, but they're always invertible n by n matrices. So in the end, what I'm saying, the left translation map, okay, by H is simply I multiply another matrix from the left. And the right translation matrix of H is simply I multiply any matrix from the right by H. That's it. It's a fancy way to say pre-multiplication and post-multiplication. But we need that to go a little bit higher. Now consider a new definition, something called the push forward of a map between manifolds. You remember the map between manifolds? I'll remind you a little bit. We said before that if I have a manifold M and a manifold N, M has points x's, x1, x2, x3, and so on. And the N has the points x1 tilde, x2 tilde, so on and so on. The tilde here has nothing to do with the tilde of the Lie algebra, just, different, just same notation, but different meaning. So here from M to N, I map from X to X tilde. So what is X tilde? Simply F acting on X. Make sense? Now a question is, and this is something I think this was in the same slide that I showed you before, and I made a comment on it, but then I quickly skipped it, which is, if I have a vector here, V, that's tangent, okay, to the curve at the point X1, and the point X1 will be mapped here to X1 tilde, and this whole curve will also be mapped here to another curve called gamma tilde. What is the relation between a vector here and the vector here, V tilde? Sorry? It cannot be through the F, you see, because the F maps from M to N, from a manifold to a manifold. And this is why we're going to be introducing this new map called the push forward of X at the point X, which will map any vector in the tangent space to M at X to the tangent space to N at the point F of X. They all have to match, because X here is mapped to X tilde, right? So, and V here is an element of TXM, and V tilde here is an element of Tx tilde N, while X tilde is simply F of X. Does everything match? Make sense? No. Yes or no? We're going to be building on this in the next slide. So if not, I can repeat it again. Who wants to repeat again? Yeah. That's right. That's exactly what this does. It relates vector in this space to vectors in that space. And these 2 points, X1 and X1 tilde, are related by the F. You see, it makes sense, right? So the points themselves are related by F, while the vectors are related by the push forward of F. Yeah.
So this map can work with the whole tangent function, not only this.
Yeah, exactly. That's why you have it. It's defined here for every point X. You can take this map and you can make something bigger on the bundle, and it will exactly make sense. It's exactly what you're saying. So in the end, I can create a new map. Okay, let's call it F star without the X, and it will map. It will be from Tm to Tn, and it will be defined in exactly this way. So if you tell me, for example, I have a vector V at the point X, I'm gonna be mapping it through this one. You see, this is why we write actually the X here explicitly. Okay, this is just to be very precise. Now let's apply what we just learned. There's a lot of notation here, and you need a little bit of time writing it yourself. Okay, I'm just gonna give you the flashlight right now. Okay, very very quick. You need to go at home and try to write it down. You'll find everything. Hopefully, if there are no errors in the slides, you're gonna find actually it all matches. So we said this is for any map. You agree? For any map between two manifolds. Any smooth map, of course, between manifolds. You see here we're talking about differentiation. That's why we need the differentiability, the smoothness of the map. Now we have a map. We have two maps we just defined, which is LH that goes from G to G. So how can we define the push forward of this left translation map? It will simply eat any vector here which is Q dot, and it will map it to the point where I'm going to go after I apply H from the left. And the same also here. What is the VL and the VR? It doesn't matter. Just exactly in the abstract picture. What was V tilde here? It doesn't matter. It's just, where you go, how you're mapped. It doesn't matter what, what the nature of it is. So here, what we're going to be calling the element, the vector that you get on the other side is simply VL and VR, abstractly. Okay? So far, so good. I know it's a lot of abstraction, but you're going to be seeing in a bit where we're going. Pay attention. What happens, think about it. What happens if we choose H to be Q inverse? What happens if we choose H to be Q inverse? What do we get? We're going to be mapping vectors here to the tangent space. What is Q inverse with a binary operation with Q? The identity element. This actually was the definition of the inverse. You remember? The inverse is that if I act with the group operation between the element and its inverse, I always get the identity. So if we choose here H to be Q inverse, you see that's exactly what we have here. So this is the left inverse. With the element Q is the left, sorry, is the push forward. So this is how you read it. It's a mouthful. You say this is the push forward at the point Q of the left translation map at the point Q inverse. This is how you write. So I'm going to be starting from the tangent space to G at Q, and I'm going to go into the identity. What is the tangent space to the identity? The algebra in general. We're still very abstract. We're not talking about SO3 and SE3 yet. Of course, that's the next step. But this is very general. This is the case for any Lie group. And you have also the same for the RQ inverse. So you see, what do we have right now? In front of you, we have two maps. They are called they have very long names. Let's call this map L and map R. Map L will take you from, it will map any vector that you have in the tangent space at Q to a Lie algebra element. While this other map R, will map the same vector, Q dot, to a different element in the same algebra. So I have two maps that I can take a vector here, Q dot, and I go to the algebra. So going back to the picture that we discussed earlier, for SO3. You remember you said that how do we relate the R dot to the elements omega tilde in the algebra? You have two ways. So here, for any given element R, we have that the L, the left translation map, is simply matrix multiplication from the left. We said that earlier. And the R, sorry, this is actually a typo. This should be, no, sorry, this is the R, should be matrix multiplication from the right. What about the push forward of the left, translation map? It's also matrix multiplication from the left. And the R, push forward of the R, is also matrix multiplication from the right. What you see here in the second lines is only a special case of the general theory I showed you. So only if you have a matrix Lie group that these two maps, they are simply just multiplying a matrix from the left or matrix from the right. How does that look like? You have this case. Take a very close look about what you see here and pay attention to the colors. When we're working in robotics, you're going to be seeing a lot these two pairs. This matrix multiplication. You can have a matrix R transpose multiplied by another matrix from the left, like this, or I can have matrix multiplication from the right. They mean different things, by the way. In robotics, they mean different things. And you can also see something like this, where I can be multiplying from the left the same matrix R transpose, and here from the right, the same matrix R transpose. What is the only difference here that you see? Exactly. That's exactly the only difference. What you see here on this part is that the r dot is a vector. It's an r dot. It's a vector. While r bar here is just a name for another element, any other element in your other rotation matrix. Okay. Can we do the same for homogeneous transformations? There is no, not yet. What you see here is you give me a matrix R transpose, call it R1, and another matrix, call it R2. What I do here is simply I multiply R1 from the left by R2. And here, R1 multiplied by R2, but from the right. So here this is R1, R2, this is R2, R1. Both are elements. Both are elements from SO3. You see here, if you go back to the left translation map, it was only working with elements. There was no derivatives. The derivative is only when you talk about the push forward. And this is what you see here. The push forward will take you from an R dot to where, now pay attention now. Where does this combination live? It has to always live in the Lie algebra. In other words, R transpose multiplied by R dot is always a what type of matrix? What it will look like? It will always be a skew symmetric matrix, no matter what the R is. Any rotation matrix, you multiply any derivative of the rotation matrix, you multiply it from the left by the transpose of the same rotation matrix. You see, everything here is the same R. See here we have R transpose and we have R and we have R dot. R dot is in the tangent space of R, and R transpose is the inverse of the element we're talking about. You see, this is the choice we had to make so that we can go from R dot to the algebra. This is a skew symmetric matrix, and this is another skew symmetric matrix. Both of them are in the algebra. Different meanings. What is the meaning of this and what's the meaning of that? I'm going to tell you in a bit, hopefully, inshallah. Yes.
The others are not skew symmetric matrices.
They are not even, they are just in SO3. Is it necessary to be, if you have an element in SO3 to be a skew symmetric?
Skew symmetric because they are an element in S(O)(3).
This is different, completely different. The math is the same. Your math is the same, to be proper. If you, before taking this course, and if you've seen this, something like this, you'll say, okay, very easy. 3 by 3 matrix multiplied by 3 by 3 matrix. Same math, right? And here, 3 by 3 matrix, 3 by 3 matrix, everything is the same, right? You don't need any differential geometry. Now, I think now you do, okay? Just to really understand what's going on. Okay? The math is very simple. We're just multiplying two matrices by each other. The point I'm trying to make here is that each one of these matrices means something different. It's a completely different object. The math operation in the end is the same, but the physical meaning of every one of these elements, the nature, the mathematical nature of it is completely different. And now let's take this and go from SO3 to SA3. How different do you think it will be? Exactly the same. Exactly the same. Nothing else. Okay. Again, this was a very easy slide to make. It will take you some time to read at home, okay? But you can, okay, you'll see everything is exactly the same. Okay? Left multiplication, right multiplication. I get an element of the algebra, and so on and so forth. Okay? Clear? Okay.
We have mentioned we have two different representations of angular velocity.
Absolutely.
Maybe use which one and which one.
Absolutely. Exactly. These two, okay, they are different numbers for the same thing. And that's exactly what we're going to be talking about right now. Okay. First, I'm going to tell you a little bit about, okay, this is just a wrapping, okay, of what we have. When we start putting indices, so something about here, okay, when you're studying this, you'll find we did not use any indices. Okay, I never told you R is which frame to what frame. Okay, I just told you R abstractly, and everything here holds. We're going to be putting indices now, and things will start to make sense. Okay, even though the math, okay, will apply to any choice of indices, but once you start to put the indices, the choice we're going to have right now, you're going to be seeing immediately what's the physical meaning from these two representations, and what does everything. Hopefully, everything here will be clearer in a bit. Okay, so bear with me. Now remember what we said about if I have the physical space. So forget about the abstract space. This is the physical space. I have one frame, the body fixed frame, and I have another frame, which is the one in blue here, which is the fixed, the inertial frame. Okay, we're talking about rotations only. So these two frames, they don't change their origin. They only rotate. So in other words, B here rotates only in its place. Make sense? How do I represent the relative orientation of B with respect to S at any time? It will always be an element of SO3, right? It will just be a 3 by 3 matrix. If I want to look at S with respect to B, what it will be? The transpose of that one. Make sense? Okay. So how B changes with respect to S is simply the transpose of how S changes with respect to B. Make sense? What is the rate of change of this element, of this configuration? If this is the configuration now of a rigid body rotating, the rate of change of the configuration will be R dot. You know now where it lives. And now we have two types of angular velocities, or in other words, two representations of angular velocity. One which is called the body angular velocity, which is the angular velocity of body of the frame B with respect to frame S is expressed in frame B. How do you calculate it? You multiply R dot from the left by its transpose to get this element. And we have another representation of the angular velocity, what we call the spatial angular velocity, okay, which is the angular velocity of frame B with respect to frame S expressed in frame S, the fixed one. This one. And how is it related to the R dot? By multiplying from the right by the transpose of this, of the RB with respect to S. Take a look at it and, you know, contemplate a little bit. All of this math, in the end, you can actually forget about it. Okay? I don't know how you're going to be sleeping at night. Okay, but okay. I cannot. So you can easily memorize a very simple rule. And it's exactly the same rule I told you before. S with S, B with B. They always have to match. Okay? And if you want to know whether I'm in S or in B, take a look at the one on the top here. So this is expressed, you see here in B, because this is the one on the top here. This is expressed in S because this is the one on the top. Which one should have the dot? The one that has the dot should be, is it this one or that one? I have here from B to S, so the B to S will always have the dot. Okay? Any 5th grader can memorize it. And you don't need to know anything about differential geometry. That's it. Any questions? Yes.
We only get in the BSB and FSB.
Yeah.
Are they just, do they differ just in magnitude, like the number, or does, for example, the body angular velocity change with time? Like
that's a very good question. And that's why we're going to be removing it. If I remove the B here and the S here, what am I left with? Angular velocity of B with respect to S, right? Without any numbers. So it's not an Rn or something, right? It's just an abstract vector. That's exactly the picture you see there. This is a very physical, it's a physical vector in space. You remember free vectors that don't have numbers? Where am I moving now? This direction. Where am I moving now? That direction, without any numbers. This is a direction of how frame B is rotating. So this is the axis around frame B is rotating. For example, if I choose omega BS to be aligned with ZS, okay, I have to bring, let's see. Okay, so thanks to Tarek, he made them actually portable, so actually I can put them in the bag without, you know, screwing it. So this is the Z. Okay, if I choose the omega is this vector. I can choose it anywhere. It's any vector in R3. This is the vector I'm going to rotate around. If I choose it like this, how is this frame going to rotate? How is it going to change? Like this. If I choose it like this, how is it going to rotate? If I choose it like this, how is it going to rotate? If I choose it in the middle, how is it going to rotate? It makes like this, and so on and so forth. Make sense?
Rotate around X, then rotate around Y.
I don't want to go there. You're thinking about Euler angles, the worst invention of humanity, in my opinion. Okay, Euler did a lot of nice things, and all of the bad things, in my opinion, are actually attributed to his name. Okay, so Euler backward integration, forward integration, they are horrible ways of doing discretization. Euler angles are horrible ways. Okay, so let's not go there. Okay, if you want, we can discuss offline. Yes.
The orientation of omega, this is they do not change.
If we change,
Let's say Z or Y or X.
okay.
This is on omega change. They remain the same.
No, the same. Because the physical, it's the same physical meaning. This vector describes how the black frame changes with respect to the blue frame. That's it.
But this is based on omega or on R. We cannot find out along which axis it is rotating the entire frame. Along which
It's a good point. It's a good point. You can do it. I'll tell you just very quickly. I'm gonna comment on it. It's the magnitude. It's the unit vector that corresponds to the vector, and the magnitude will be how fast you're rotating around that. Okay, I'm not gonna talk more about it. Okay. Yes.
Don't get the difference between the spatial angular velocity and body angular velocity.
If you don't get the difference, I agree. We haven't talked about the difference. But do you see, are they the same element? They are different mathematically, right? Why? If you can, what is the property here that we're using? It does not commute. That's it. So these two, they don't commute, which means that the numbers I get here are different from the numbers I get here. Why is this body angular velocity and why is this spatial angular velocity? You should answer that question in the homework. Okay? So you have to wait for that. I cannot show you yet. I'm just telling you they are two different objects. Okay? Omega 1 tilde and omega 2 tilde. And what's this whole point of the tilde, right? Something I hope we have time to look at it today. Another thing, can we go from SO3, which is rotations, to translations and rotations? General rigid body motion, how does it change? Like this. So if I have a robotic system, this complicated robotic system, the robot arm is moving and the end effector, and I have the base, and I have two drones, and I have cameras and sensors and so on and so forth. How is it easy to relate stuff? This is the simple equation that you have. Okay, there's nothing else, by the way. That's it. You can do with this very simple equation, again, which a 5th grader can memorize. Okay, the only thing now is that we have new objects that you have never seen before. You've played around with angular velocities, okay, hopefully in your mechanics course, but you've never worked with these objects before. Okay? So these are called the twist. Exactly the same way this one is the twist, which is represented in the B frame, and this corresponds to the twist that is represented in the S frame. What is the twist? How does it look like inside and stuff like this? That's what we're going to be doing next. Now some properties to see really how powerful this tool is. To have this complicated system, and I'm interested in not, so for any of these frames, so I and J and K and M and all, they can be any frames, right? The end effector with respect to the base with respect to the camera with respect to target, anything, it doesn't matter. If I'm talking about the angular velocity of frame I with respect to frame K expressed in anything, and I want to know the K with respect to I, what do? Minus sign. If I know about I with respect to M, and I want to know about I with respect to K, what should I add here? Just add M with respect to K. You see here, these have to cancel out. So if I want to know I with respect to K, expressed in any frame, I just take I with respect to M plus M with respect to K, and I add them together. Because we're talking about something else. What we're talking about now is that what you're talking about is the relative pose, right? Which was, if you know where the end effector, okay, is with respect to the base, and you want to know the end effector with respect to the inertial frame, okay, then you need to know the pose of the base with respect to the inertial frame, and you do the multiplication. But what if the base is moving around? in general 3D. It can even be flying. And the end effector is also moving. So the robot arm and the base are moving at the same time. So what if I want to relate the twist of this one with respect to the inertial frame to the twist of this one with respect to the inertial frame, and I also know the twist of this one with respect to the inertial frame. How do I relate to them? Exactly. I just add them together. Why of a sudden we're talking about addition now? What is the vector? What is the? I already said. What is the structure we're talking? What the structure that algebras have? A vector space structure. And a vector space structure has this idea of plus and minus. I can multiply by 2, by 3, by -1. I can add two vectors together. There is just one catch here. Can anyone get it from the slide? There's a very important restriction. Which indices? What about it?
We had left and right combination, now it's the opposite.
No, you can just write this here and this here. Doesn't matter. What order? That's exactly what he's saying. No, it does. Plus is bijective. Plus is commutative. This is the plus. We're talking about the algebra. It doesn't matter.
But it doesn't make sense.
Why?
Twists, yeah.
So if I say m with respect to k plus I with respect to m, it's not the same. So okay, let me say it to you in another way. If I have two 4x4 matrices and I have A plus B and I get B plus A, you don't get the same thing? Doesn't matter. What is the catch here?
They are additive inverse, right?
They are additive inverse, yeah. But that's not the catch. There's a very important catch. The green star. It has to be the same frame. What? The green star, what is it? Where you express these numbers. So for example, if I'm expressing m with respect to k in frame k, I cannot add it to I with respect to m in frame I or m or something else. Okay, if this was m with respect to k in k, and this is I with respect to m in k, then I get here I with respect to k in k, and so on and so forth. Exactly. They should all be in the same vector space. And that's what, okay, I'll not comment on that because it will take some time. Yes, we do have, they should all be in the same frame. Think about it this way. Because in the end, they're all 4x4 matrices. And these here are all skew symmetric 3x3 matrices. So as numbers, you can add them together. But that's the discrepancy between just having numbers and having the physical meaning behind it. Okay, so if you have numbers, okay, you cannot do stuff with it. If you have matrices, of course, you can do everything. But now the matrices they are just numbers that correspond to some physical object behind it. You always need to pay attention to what is the physical object so that you can know what is the permitted operations and not on these numbers that represent it.
That's why you cannot mix between the body angular velocity and the spatial angular.
Absolutely. There's no such thing as this. I'll even give you something even harder than that. Without any comments. What if you all know what a gyroscope is? If you have a drone, the first thing you do on it, you put an IMU. If you know what it means, okay. If not, I'm not gonna discuss it. You can talk about it offline. You have a drone and you put on it an IMU. The IMU has gyroscopes on it. The gyroscopes, they measure the angular velocity. In the end, they're going to be giving you three numbers for the angular velocity: omega 1, omega 2, and omega 3. Omega x and y and z. Three numbers. Do you think they correspond to this one or to that one? The angular velocity, the numbers that you get from the gyroscopes, do they correspond to the angular velocity in the body frame or the angular velocity in the spatial frame? No, in the body frame. Because the sensor itself rotates with the body, right? It doesn't care where you are. It doesn't care how, what the spatial frame is. It doesn't even know it, right? It doesn't know how you chose, if you chose which is positive and which is negative. Okay? What is x and what is y and so on. But on the body itself, okay, it already knows that this is the forward, this is the right, and this is the left, and so on and so forth. Another thing, but this will even complicate it more. It will confuse you more, but I'll not comment on it. If I have gyroscope values, can I integrate them? They're angular velocities, right? omega 1 and omega 2 and omega 3. You all took in mechanics that the rate of change of angle is angular velocity. So theta dot is equal to omega. If I have omega, can I integrate it to get theta? You know, it's very easy, you know, just a number, you know. Take the previous value, add plus delta t, multiply by the omega and stuff like this. Double integration, right? And stuff like this. Completely nonsense. Completely rubbish. Doesn't make any sense.
This structure.
Excellent point. You don't have this picture. You see here, an element of the algebra, which is the angular velocity we're talking about, is not the tangent to any curve. That's why you see here, which shows this notation r dot. It's a dot of something, but this is not a dot of anything, which means I cannot integrate it to get this something. The r dot, I can integrate it to get the r, but the omega tilde, I cannot integrate to get anything. It's rubbish. Mathematically, you can do it. Calculate it. You're going to get rubbish. Doesn't mean anything. Because that is what you get from the gyroscope. Absolutely. And internally, what you have is something like this. So you take the r, you say that I can integrate the r dot. So I get the readings from the gyroscope, multiply it. You know, I'm going to take this side, this one here on this side. I'm going to multiply this by that. I'm going to get the dot, and then I integrate the dot. That's exactly what you do in the imine. But the omega tilde, I don't integrate it directly. I'm not going to take any more time from this, okay? Okay, good. So we're on time. Okay, so we have 20 minutes to go to the board to really show you what are all of these, you know, mysterious objects we talked about. Okay, I gave you a little bit, you know, we're going to be looking at numbers. Yes. Excellent question. Of course they are. Of course there are. So the question is, if I have some omega tilde in a frame, can I relate it to any other frame? Yes. If I have some twist in a frame, can I relate it to any other frame? Yes. Do you think it would be the same map? Abstractly, in other words. If I have a Lie algebra element and I wanted to map it to another Lie algebra element, okay, can I, okay, if they have the same meaning, yes, exactly. If they are in the same vector space, they are expressed in the same value. No, even if they are different. No, here they are different. We're going to be having here something called the adjoint map that will map elements of the algebra to elements of the algebra. The adjoint map, we're going to have one for SO3 and we're going to have one for SE3. How the adjoint map itself is defined abstractly will hold for any Lie group. But of course, how it looks for rotation matrices and for translations one will be different. Okay? So just the map itself will look different, but the physical meaning, okay, will be the same. And by the way, okay, no, I'll not say it. Okay. So let's go to the board now to tell you a little bit about these elements we're talking about. The first thing we're going to be doing is that angular velocities, this tilde angular velocities, okay, the skew symmetric matrices. There is something we discussed before, which is if omega, no matter what the indices are, forget about the indices now, if it's in small SO3, which means it's a skew symmetric matrix, how does it look like? You should know that. It should have what on the diagonal? It's 3 zeros. And then we're going to have, it's going to consist of 3 numbers, 3 unique numbers. Omega, let's call them omega 1 minus, and here it has to be minus omega 1. Here it has to be omega 2 minus omega 2, omega 3 minus omega 3. If you look at this and you say, you know what? I can think of a very trivial map that will take any skew symmetric matrix and give you what? What can you think about? Who can continue this sentence? If I give you any skew symmetric 3 by 3 matrix, what can you give me as a result? No, the transpose will be the minus, so there's no new information. 3 numbers, omega 1, omega 2, omega 3, that live in R3. What does that tell you? No, but what does that tell you about SO3? It's isomorphic to R3. What level of isomorphism? You see, as a set, this is a bijective map going back and forth. We're going to be calling this map, by the way, we're going to be calling it S. So the map that will, actually, we're going to be calling this S inverse. Well, okay, to be precise, we're going to be calling the map, if you give me any 3 numbers, like this, and you tell me construct for me a skew symmetric matrix, I can simply do it like that. We're going to be calling this map S. Make sense? Very easy. And this tells you that these two are isomorphic to each other. If I have 2 omega 1, if I call this omega but without a tilde, okay? So you see here, this is omega tilde, and this is omega without a tilde, just 3 numbers. That's exactly what you know about angular velocity, right? It's omega x, omega y, omega z. Angular velocity about the first axis, the second axis, and the third axis. That's exactly what you see here. 3 numbers. This is just a skew symmetric formulation of it. Okay. Now, something I hope it doesn't confuse you, but maybe it will explain stuff. This is something you have to show for yourself in the assignment. That if I have an SO2, how does it always look like? It will always look like something like this. Any skew symmetric matrix, this is a 2 by 2 skew symmetric matrix, has to always look like this. No other way. Okay. Which means that what can you deduce from this? It's exactly 1 number. And of course that makes sense, right? You remember what was SO2? It was like rotation in 1 frame, right? It's rotation, like a rotation around the Z. Okay. Imagine that you have a mobile robot on the ground. What does it always do? Only rotate around the Z, right? Oh, that's the Z. It only rotates around the Z, right? It has an angular velocity around the Z. Only one thing, omega. And that omega is the same. You always say that omega is theta dot. And I integrate the theta. Okay. So if you have in 2 dimensions, okay, omega is simply just 1 number. In 3 dimensions is something else.
In a single dimension SO1, no numbers, like we cannot rotate.
SO1, there's no such thing as S. It will be a degenerate case. I haven't thought about it actually. It's a good exercise. Yes, but it will not be R. It will. I don't remember how. You will still gonna get. You can still have something called a 4 by 4 skew symmetric matrix, but it will not have 4 numbers. It will have, I think, a little bit more. There was a simple calculation. I think it was like n multiplied by n minus 1 divided by 2, something like it. But I'm not sure. I have to remember. Yes, exactly. Absolutely. Yes. Weird stuff. For example, no, that's something else. Oh, but yeah, you're right. The math works for any n. Question? Any questions? Okay. So this is the skew symmetric matrices. So in the end, what you have here as this SO3 is nothing else than just the 3 numbers you're used to, just written in a skew symmetric form. And now the relation we're talking about, that R dot multiplied by R transpose is equal to omega tilde, okay, or R dot multiplied by R transpose here by another omega tilde. For example, this will be one expressed in the B frame. This will be one expressed in the, no, yeah, that's one in the S frame. Then if I give you this 3 by 3 skew symmetric matrix, you can in the end convert it to just omega 1, omega, no, so you can just convert it to omega in the B frame. And you can convert this to omega in the S frame. Now the question of Tariq, okay, rightfully was, How can I relate these two together, right? Is there a map that will transform this one to that one? The answer is yes. Okay. Okay. And this you're gonna have in the homework. Okay. So these two together are related by what's known as the adjoint map. Can we take the same picture and go to SE3? Yeah. So in SE3, we're going to be doing a little bit different. Okay. What I'm going to do now for SO3 is that I'm going to start by saying, okay, we said that V tilde, for example, of B with respect to S expressed in B is actually defined as H dot, H. What? Who said transpose? Not transpose, okay? I have H multiplied by H dot to memorize the rule, right? I look at here, I see this is B and this is S, so this has to be and this has to be S, okay? Okay, right, in other words, okay, let's go back. The way you fill in this is the following. I look at this index first. So first of all, okay, this is just the second part where we're talking about the twists. So this is the V tilde. Okay, I look at this index, this one here, the B. And you remember what we said? That this one has to be a B. And if this one has to be, this one has to be, and this one has to be, and this one has to be, where should the dot go? I look at here, I find this is B with respect to S, then the dot should be here. Full stop. That's it.
I think it's always B.
No, because I can have B with respect to S expressed in S. No, I mean, if you follow this, algorithm, where should the dot be? Should it be on the right or the left? If you don't want to memorize left and right and stuff like this. If you want to memorize it, body, fixed frame, okay, so which is the one that was the down here. If this is B with respect to S and I want to express it in the one that's down will be left. And the one on the top will be right. Okay. Again, so different ways to memorize the same thing.
We will put the top H.
No, it will always be BS, but you'll have this two swap together. Okay, the dot is always on B with respect to S. Okay, so now we're talking about this element, which is the one expressed in the B, and now let's see how does it look like. First of all, you all know what H BS looks like, right? It's R BS, psi BS. Make sense? Okay. What about H dot? It's a abstract vector, okay, but not your vector, okay? But if you want to think about it in terms of math, it will be what type of matrix? 4x4 matrix. This was a 4x4 matrix. We're going to be working in SE3 here, okay, just for simplicity now. It will take us more time to talk about SE2. By the way, SE3 is easier, by the way, than SE2. Imagine, okay, believe it or not. So HB from B to S dot will be RB to S dot and psi B with respect to S dot. What about the last row? 0 and what is the differentiation of 1? A constant. Just 0. Okay? Now now we want to multiply this by that. Is that correct? No. We want to multiply the inverse of this by that from the left. So what is the inverse of this? So what is H? What is yes, exactly. So what is HS to be, which is nothing else than HB with respect to S, but the inverse. What do we have here? We have RS with respect to B. RS with respect to B is the transpose of B with respect to S. You're going to have a lot of these indices. We're going to have much more than this, okay, later on, but you're going to be playing around in the assignment in the home, okay? We're going to have minus RSB multiplied by BS. And we're going to have here 0 and 1, okay? You can never make mistakes here. Why? Because if this is B with respect to S, it should always be multiplied by something that takes you from S to B. You'd always find this the case, okay? So now I have this matrix and I want to multiply it by that matrix, okay, from the left. Okay? So what do we have? So this should be, now I'm going to be a little bit fast, and then you can follow on your own at home, inshallah. So then we have this one. So the way you work with this, I know you're very good about doing matrix multiplication, right? But you're very comfortable with just, seeing numbers, doing rows by columns. What we have here is actually we have blocks. So this is actually a block, and this is a vector. So this is a 3 by 3 block. This is a 1 by 3 matrix. This is a 3 by 1 vector, and this is a 1 by 1 number. Okay, but still the rule holds. I can multiply this row by that, so this row block by this column block, and so on and so forth. So actually, the result that you get here is simply this one multiplied by that one, plus this one multiplied by that one. Okay, and just for the units to match, so for the dimensions to match, this is actually a 1 times 3. 1 times 3, and this is a 3 times 1. So what do you get? 3 times 1 multiplied by 0 times 1, 1 times 3. I get a matrix of 0 by 3 by 3. That's why it's just, I have plus here, 3 by 3, 0 matrix. Nothing else happens. And then on the top, we have that psi bs dot minus, sorry, actually we have, what is that? We have this one multiplied by that one. And we have this one multiplied by 0. And on the bottom, we have 0, 1 multiplied by 0, 0. So we just get zeros and zeros. Well, this is a 1 times 3, 0. Can we simplify it a little bit?
Yes, sir.
Yeah?
What you talked about, where the bottom part of one will have to correspond with the top part of it, has kind of been violated in this.
Where? In this one? Yes, of course. That's why, yeah, because this is not correct. Yes, you're absolutely right. This one, I should have taken this element, which is S to B. You're right, absolutely right. This should be S to B. And this should be S to B. Okay? And this was completely, okay, I did not mean it, but you see immediately you can never make mistakes. Okay? So that's why I put a lot of grades on this, okay? Yes. That's a good point. So now that's something else that we've seen this term alone by itself, right? Where we said that this term is actually what we called, you see here, if this is BS dot SBH, and this is BS dot, and this is SB, but all of this is R, then this should be this term. It's a skew-symmetric term. And then I have zeros and 0, and I have a term here. What's the dimension of this term? It's a 3 by 1. It's just a vector. We're going to be calling this vector small v. This is a capital V, capital curly V, which we'll call the twist. And this is a small v, which you call the, if this is what you call angular velocity, what is this? Linear velocity. So this is exactly how an element of SE3 will look like, because this is exactly what the V tilde looks like. Okay? If I calculate, and this is the left for you as a homework, if you calculate V tilde B with respect to S but expressed in S, you're going to find that it's also can be written as an omega B with respect to S expressed in S, and here V, another element, okay, a 3 by 1 vector that we're going to be calling linear velocity of B with respect to S expressed in S, and this would be the other V algebra element. Okay. Now I'm going to go a little bit step further. That's the last thing I promised for today, is that if I have this V tilde, B with respect to S expressed in B, and we say that in the end it looks like omega and V B S, and this is 0 and this is 0. And we said that we have the V B with respect to S expressed in S, and this is simply two elements here, S and S, 0 and 0, B, S and S. What does this tell you about the vector space SE3? In the end, yes, it's a 4x4 matrix that has all of this stuff, but it's isomorphic to what? It's isomorphic to the pair of omega tilde alone and V, right? Where this lives in SO3 cross R3. You all agree? And this element is that I just showed you earlier that omega tilde by itself is actually isomorphic to R3. So I can also map this one to omega and V, which lives in R3 times R3. And if I have three numbers and three numbers, I can put them together and you get what? One element that has 6 numbers that we can call capital V that lives in R6. And this is exactly the vector that corresponds to your vector, 6 numbers that corresponds to the generalized velocity. Angular velocity and linear velocity in one object. Just like how the H, how much time? I think we're over time, right? Yeah, okay, so we're right on time. I'll just wrap up. So just like how the H itself corresponded to rotation and translation, to orientation and displacement, then the algebra SE3 will correspond to the velocity, the angular velocity, and the linear velocity all in one object that's called the twist. Okay. And of course, all of the indices here, I'll just add them to be complete. We have B, BS, B, BS, B, BS, and then this will be BS. And of course, in the same way, I can just map this to what's known as the twist in the spatial frame. It's also in R6. And what do you think both of them will be related by? What's known as that joint map. And more on that later, inshallah. Yes. Excellent question. Excellent question. Let me rephrase the question. So, is SE3 isomorphic to SO3 cross R3 as a set, or as a group, or as a vector space, or at what structure is it isomorphic? More on that later. The cross is right. We're going to leave it as a cross right now, okay? Because this is just as a set. Okay? So as a vector space, they are. As a Lie algebra, they're not. And now you say, okay, but what's the difference between Lie algebra and a vector space? And that's not something we discussed. I'll leave that for you on your homework. If you want to, not like homework after the homework, okay, that your own time, you can read about it and you can check where does it break, okay? But I have to stop now, okay, for time. Okay, Jazakumullah khair. Assalamu alaikum.